Switching to full screen. All right. Whoa, I'm stuck. There we go. Okay, area of a trapezoid. I'm hoping that you all remember from your wonderful geometry teachers the formula for area of a trapezoid. So, area of a trapezoid, just in general, not this one, but in general. What's the formula for area of a trapezoid? Base 1 plus base 2 divided by 2 times the height. That is fine. So a student first period said average of the bases times the height, which is another nice way to look at it. I personally tend to write it like this. I know it's kind of strung out that way, but it makes it easier for me when I'm doing the problems in calculus. So anyway, however you remember it is fine. So sum of the bases divided by 2 times the height, anything that's equivalent to that. So for this trapezoid, so we have 1/2. What's the height of the trapezoid? 5. All right, and then what are the 2 bases? 10 and 14. So we end up with 24 divided by 2, which is 12 times 5, which is 60. And if we include units, we would write inches squared, right? Okay. All right. Good, good. Looks like everybody got it. Good. We can all find area of a trapezoid. That's all you need for this lesson, right? Okay. We are going to walk. So this is, just so you know, we're in section 7-7. I know we're in chapter 5, but we are jumping to 7-7 just for this one lesson. The first problem we're going to do is kind of a big one. We're going to walk through that together. Then I'm going to give you several to do on your own or with your groups. I should mention, tomorrow morning we have PLCs. Like I know it's technically like Friday, but they're treating it as any other Tuesday. So tomorrow we have PLCs, so I'm not available tomorrow morning. Tomorrow afternoon I have a doctor's appointment, so I cannot stay after school. I'm actually leaving during court. So I'm not available before or after tomorrow. I'm not supposed to be available after school today. I actually technically have a meeting. But if students really do need help, this meeting is one where I can skip it if I need to. So anyway, if I really need to, I'll skip it and stay for you guys if you need help. All right, so are we ready? Okay, we just passed pie time, so we're good. All right. So this is from your book. You don't have to write this down. So this slide is saying why would we ever want to approximate an integral with anything, right? When we could just find the integral and get the exact answer, right? Why would we need to approximate? So there's 2 reasons that you might need to approximate an integral. The first is there are some integrals that can't be done. There are functions out there that do not have an antiderivative. E to the x squared does not have an antiderivative. There is no function in the universe whose derivative is e to the x squared. So because of that, you can't use integrals to calculate the area under e to the x squared. There's area. If you graph e to the x squared, there's graph. There's stuff under the graph. There is area under that graph. How do we calculate the area if we can't find an antiderivative? The only way to do it is to approximate it. So when you have functions and you, for some reason, need to find area under the function, if the function is not antidifferentiable, the only way to calculate the area under the curve or to antidifferentiate the function is to approximate it with rectangles or trapezoids or some other shape. All right. The other thing, is suppose you don't have a function. What if you just have a collection of data points? Oh, yes, Al.
So, like, when you said e to the x squared is impossible, does that count if it's 5 to the x squared? Is that all?
That's the same thing, yeah. That's a very good point. So I should really say a to the x squared. Yep, because 2 to the x squared also does not have an integer. Yeah, good point. So the other type of time that you might want to approximate is if you don't have a function at all, if you just have like a collection of data. So if we just have a set of data points and we want to roughly integrate a function based on the set of data points, then you might want to approximate that integral if you just have data points using rectangles or trapezoids, as opposed to finding a regression function to represent the data and then integrate the regression function. So either way, it just depends on the situation at hand. Okay, so that's why. Now, how do we approximate? Well, we've already approximated using upper and lower, which you don't really get tested on because they're not on the AP exam. But mostly left, right, and midpoint rectangles, right? We call those rectangle approximations Riemann sums. They're named after a mathematician named Bernard Riemann, who came up with the concept. However, in addition to left, right, and midpoint rectangles, we also use trapezoids. Okay. So we are going to approximate the area under this curve. So we're going to use, just, your book says use the trapezoid rule with an n number. That is the same thing as just saying use trapezoids. This is how many to use, right? Okay. So use the trapezoidal rule with n equals 5 to approximate the integral from 1 to 2 of 1 over x dx. So 1 over x dx is this, lovely flowing function, right? Pretend that's pretty. Okay, from 1 to 2. And we are going to approximate this area by splitting it and using 5 trapezoids. Now, when you use trapezoids to approximate area under a curve, so the trapezoids typically are shaped either like this or like this. However, no matter what, we take these trapezoids and we turn them sideways. So like a trapezoid on this graph would be if we took this endpoint and this endpoint and like connected them with a straight line. So what we've got then is this would be like this guy turned sideways. Now, because of that, the height of the trapezoid typically is actually the width going this way. So if we're on a traditional trapezoid and we label an h for height, that h actually ends up being the width of the trapezoids when we turn them sideways like this. So our width, like normally we have width of rectangles, our width of our trapezoids is the same as the height of the trapezoid. It's just that they're turned sideways. All right, so let's find our width / height for our trapezoids. So our width is still calculated the same way, b minus a over n, if they're all evenly spaced. So in this case, we're going from 1 to 2, so we have 2 minus 1 over 5. Our width is 1/5. When we do our trapezoidal sum, when we did a rectangle sum, I always told you guys to start by making a table. Same thing with trapezoids. It's just easier if you start by making a table. You don't have to, it's not required, but it does make your life a little bit easier. It's easier to see. All right, so this is our x, this is our y, 1 over x. You always start at your left endpoint, and then you just add widths until you hit your right endpoint. So we're walking by widths of 1/5, so we start at, oh, whoops, we're not starting at 0, we're starting at 1, sorry. This is why we do math in pencil. 1. Okay, so 1 is 5/5. So the next one we'd have would be 6/5, then 7/5, then 8/5, then 9/5, and then 10/5 or 2. Does everyone understand how we got the x values? Okay. We are plugging these into our function. Our function is 1 over x. That's like the flip it function. So what does it mean? You just flip everything over. So flip 1, you get 1, 5 6, 5 7, 5 8, 5 9, and 1/2. All right, we've made our table. We're ready to find our trapezoidal approximation. So when you do your area with trapezoids, so in my past, I was used to labeling it like by writing the word area with a little subscript of a trapezoid. Your book will shorthand this to call it T5, T sub 5, for trapezoids using 5 trapezoids, right? Okay, so our T sub 5, all right, there is one number that gets multiplied times every trapezoid in the universe. Every trapezoid in the whole universe always gets multiplied by 1/2. So you can pull the 1/2 in front. If your widths are all the same, which in this problem they are, you can pull the width out in front, just factored out of all the trapezoids. So our width is 1/5. So I'm going to pull that in front. What I have left now are the sums of the bases, which in this case are the sums of the heights. So it's like this height plus this height would be our first 2 heights we add together. So, and I will tell you, I put a bracket and then I group my sums with little parentheses. So 1 plus 5, 6 would be my first 2 heights, the heights on either side of my first trapezoid. Let's see. What would be the next the heights on either side of the next trapezoid?
5 6 5 7.
5 6 and 5 7. So if you notice, every interior height, all the middle heights, these guys get used twice. They get used, let's see, once for the trapezoid on this side and once for the trapezoid on this side. Okay. All right. So you're going to have a bunch of repeats. So then the next one would be 5 7 plus 5 8. The next one, 5 8 plus 5 9. And the next one, 5 9 plus 1/2. How many trapezoids were we supposed to have?
6.
5. That's okay. And so always check to make sure I have 5 sums of heights, right? Okay. Yeah.
Could you just do like 1 plus 2 times each of the middle ones and then plus 1?
It's a can't you just question. Yes. So yes, can't you just do left end point plus 2 times 5 6 plus 2 times 5 7 plus 2 times 8 6 5 8 times plus 2 times 5 9 plus right end point? Yes, absolutely you can. Mathematically, it's exactly the same. However, 99.2% of the time, the College Board is not going to give you evenly spaced widths. So because of that, you won't be able to do it on the AP exam. So I never do it just because I like to just stay in the same habit so that when I hit the AP exam, I'm used to writing it hard. So anyway, but yeah, you can. Like no one's going to fault you if you do that. There's nothing, as long as it's numerically equivalent, it's correct, right? Okay, so anyway, I will tell you on all scoring guidelines, the College Board always like displays it in this way so you can kind of see each trapezoid kind of as its own thing. They actually don't even put the 1/2 out front. Like they'll put this over 2, with its width in front, and this over 2 with its width in front, right? That kind of stuff. So they like to show each trapezoid separately. Okay. By the way, what is this answer? I have this. Okay. Let's see here. So this one is 1753 over 2520, which is approximately equal to 0.6956. So 0.695 or 0.696. I really should just put on my glasses. Okay. Is what this answer is roughly. Yeah, that looks right. Okay. All right. So there's our trapezoid. For some reason, your book in this section decided they really, really wanted to marry trapezoids and midpoint rectangles together. So most of your homework problems, you're asked to do the same problem using trapezoids and then using midpoint rectangles. I don't know why they decided that those two should go hand in hand, but they did. So because of that, we're going to go ahead and do midpoint rectangles on this one just so that to review, to make sure you remember how to do them, because you're going to see them in your homework tonight. So, doing the exact same region now with midpoint rectangles. So find the same approximation using midpoint 5 midpoint rectangles. Here's the thing about midpoint rectangles. So when you're doing midpoint rectangles, you still need to use a table. I'm going to make a giant table. You don't have to make a giant table, but I'm going to do it just for purposes of demonstrating what's going on. All right, so here's the thing about midpoint rectangles. The width doesn't change. That messed up a lot of groups on the first quiz with the midpoints. Is a lot of groups did, like, say we're doing left and right, right? So if I was doing, say this is my data, and I'm doing left rectangles. My first width, I'm still going from 1 to 6 fifths. It's still a fifth, and the left tells me which height to use, right? So I'd use that height on the left. But the width is still 1/5. When I'm using midpoint rectangles, the width is still 1/5. The width doesn't change. The only difference is the midpoint tells you what height to use, right? Now I'm finding the height at the midpoint. Left, I find the height on the left. Right, I find the height on the right. Midpoint, I find the height at the midpoint. It's all the only difference. Everything else, oh. I had to sneeze, it's gone. Got my eyes are watering. Oh my goodness. Okay. So anyway, the only difference is that your table has to look kind of funky because it has extra columns because they got to give you heights at the midpoints, right? So sometimes you have to kind of go, like, hop over to get to your ends of your rectangles. So anyway, all right, so we're going from 1 to 6 fifths. How do I find the midpoint between 1 and 6 fifths? Well, it's the average of the two numbers, right? 5 fifths plus 6 fifths is 11 fifths. The average would be 11 tenths. Then we'd have 13 tenths, 15 tenths, 17 tenths, and 19 tenths. I don't need all these heights. I only need the heights at the midpoints. And remember, this is the flip it function, so it's 10 elevenths, 10 thirteenths, 10 fifteenths, 10 seventeenths, 10 nineteenths. I don't need any of the other heights. All I need are the heights at the midpoints, so that's all I'm going to write. But I just want you to understand, if you had a table with all these values, and I said approximate the area using 5 midpoint rectangles, your width is still 2 minus 1 over 5. It's still 1/5. The only difference is how do you find the heights? And the heights would be the heights at each of the midpoints. So our area using midpoint rectangles, which your book will call M sub 5. So since the widths are all the same, you can pull it out front. Rectangles are nice. It's just width times height. No average divided by 2 or anything. You just width times height. So you just have to list the 5 heights. So 10 elevenths, 10 thirteenths, 10 fifteenths, 10 seventeenths, 10 nineteenths. Kabam. And I set down my glasses and my calculator. Okay. So, all right, and this equals, You'll love this fraction. 479,378 over 692,835, which is approximately equal to 0.691 or 0.692. It's 0.6919. This one was 0.6956, I think. Okay. All right. All right, trapezoid, half times the width times the sum of the bases. Rectangles, just width times height. Rectangles are easier. Any questions about trapezoids or rectangles, parts A or B? Part C says calculate the exact area. Like actually do the integral. So for part C, it was the integral from 1 to 2 of 1 over x dx. No calculators. Just take a second, everyone find the area. No calculators. You should be done. It's that fast. Yes, Keegan.
So my question would be that for this, because ln2 minus ln1, would be expected to get rid of the ln1 because
Yes.
it just equals 0?
Okay. But it's good that you knew it was ln, right? Okay. So what's the antiderivative of 1 over x?
ln of the absolute value of x.
ln absolute x from 1 to 2. Don't forget the absolute value. In this case, doesn't matter, but it does on your test. So ln2 minus ln1. But what is ln1? 0. So this is just ln2. All right, just so you know. Hey, quick question. This was 0.691. This was 0.695. What do you think the exact area was?
0.693.
It is 0.693. It's approximately 0.693. I think it's 0.6931. Okay. Oh, someone said yeah. All right. All right. So that's your exact. Last question. Is the trapezoidal approximation an over or an underestimate?
Over.
Wow. Yes and yes. Like yes to all of it. Okay. So in case you've forgotten my amazing memory trick, rectangles go with direction for over and underestimates. Tangent lines and trapezoids go with concavity. So tangent, if it was a tangent line, right, we would draw, like all I would do is just draw a, this is, by the way, is this function concave down or concave up? It's concave up like a cup, right, down like a crown. Doesn't matter, that's decreasing. Concave up, right? So if I have a concave up function, if I'm doing a tangent line approximation, it would be below, right? Just draw a concave up function with a little line. Okay, but for this is a trapezoid. So just put 2 dots on a concave up function and connect them. Is your trapezoid above or below? It's above, right? So how would we answer this? We would say that T sub 5 is an overestimate of the actual value because y equals 1 over x is, I'm going to abbreviate concave up on the interval from 1 to 2. Yes, Casper?
Would we have to know that for the test?
The over and under thing? Yes.
Okay.
And the AP exam.
Got it.
And your final. Yes.
So
No, it's no.
Yes, you just need to know.
okay.
Okay. Good. Any other questions before you guys try one on your own or with your groups? All right, let's do it. Okay. Use the trapezoid rule. I'm going to give you a tiny bit of guidance. Use the trapezoid rule with n equals 6 to approximate the area of the region bounded between y equals 6x minus x squared and the x-axis. Did I give you left and right endpoints? No. Does that mean there are no left and right endpoints? No. There are left and right endpoints. You just have to figure them out. How are you going to figure them out? Well, you got to figure out, because it's a region bounded between those two graphs. So you got to find where 6x minus x squared and the x-axis meet. All right? I will tell you, I scolded a lot of people in first period because there were quite a few who did a great big math no-no when they were solving the equation that they had written. And so, should I pre-scold you in advance so that you don't do it?
No.
You know what it is? Yes! They did. I know. Doesn't that make you mad? Yeah.
Why would you do that?
I know. That's what I say, right? Okay. We never, ever, ever divide out a variable when we are solving an equation. What do we do? What's our favorite F word? We factor. We never just randomly divide out an X because you lose a solution. You take it from it is disgusting. Yes. You take it from a quadratic to a linear, you go from two solutions to one solution. It's totally wrong. It's bad math. We don't do that in this room, right? Okay. All right. So have a step. So if you figured it out, you get this shape from 0 to 6, right? Roughly. Okay, so you have this upside down parabola from 0 to 6. How did we figure out the 0 and the 6? Well, what is every y value on the x-axis? Anywhere on the x-axis, what's the y value? 0, right? So you set your y equal to 0. We factor, and we get two beautiful solutions that are both equally important, 0 and 6, right? Okay, so those are your left and right endpoints. Our width of our trapezoids is 6 minus 0 over 6, or 1. You're welcome. All right, so then we do our table. So we have an x and a y, 0, 1, 2, 3, 4, 5, 6. All right, and we plug into our function. 0 is 0, 6 minus 1 is 5, 12 minus 4 is 8, 18 minus 9 is 9, and then it is symmetric, and you can just repeat backwards, and you're done with your table. And our trapezoid sum, t sub 6, is equal to 1/2 times the width times, so 6 trapezoids, 6 sums, so 0 plus 5 plus 5 plus 8 plus 8 plus 9 plus 9 plus 8 plus 8 plus 5 plus 5 plus 0. Couple quick comments. On a lot of papers, I saw 5 plus 13 plus 17 plus 17 plus 13 plus 5. The College Board wants to see the heights. They also want to see the width. Like, even though the width is 1, you have to write it. And if one of your heights is 0, you have to write it. They want to see this stuff, even if it's a 1, even if it's a 0, they want to see it. So be very careful and very meticulous. Don't be lazy when you're writing out your work for your trapezoids, because there's only going to be 1, if that, on the AP exam. Just do it. So write it out. If you do the math right, you get 35. So yes.
Would it be like cheating if you skip that stuff entirely, just sum them together first without even like showing that as two separate values?
I'm 99% sure they're going to want to see the separate values.
Okay.
Just honestly, it's not like they're going to ask you 12 trapezoid questions, right? They'll only ask you one, if that. Just do it. Just write them out. Okay. One other little thing I want to mention before we answer the over-underestimate thing. If we sketch the trapezoids, okay, so our first trapezoid looks like that. The left height is 0, the right height is 5. Is this a trapezoid?
It's a triangle.
It's a triangle, right? But all triangles are trapezoids with one of the bases being 0, right? Right? Because if you take area of a trapezoid, 1/2 times the height times the sum of the bases, right? If one of the bases is 0, you just have 1/2 base times height, right? So a triangle is just a trapezoid with a base of 0, right? Okay. Yeah, so it's okay if you have a triangle. Triangles are fine. They're all triangles are really trapezoids. Okay. All right. All trapezoids are what? Not all of them are born quadrilaterals. We don't discriminate against a 3-sided trapezoid, right? Okay. All right. So, over or underestimate. Is this shape concave up or concave down?
Concave down.
Concave down. So, is this going to be an over or an underestimate? This is an under. So, T sub 6 is an underestimate or less than the actual area of the actual area. Because y equals 6x minus x squared is concave down. And it's concave down everywhere, so we just write that. Okay, good. Any questions on this one? One more on paper before we move to whiteboards. All right, no calculators. Fun with trig. Okay? So all right, so 4 trapezoids. So our width is pi minus 0 over 4, or pi fourths. So if we make a table, so we have x and we have sine x, or sinks. All right, so we start at 0 and we walk by pi fourths. Pi fourths, pi halves, 3 pi fourths, and pi. What's the sign of 0?
0.
0. Anyone know the sign of pi fourths?
Root 2 over 2.
Root 2 over 2. What's the sign of pi halves? 1. 3 pi fourths?
Root 2.
Positive or negative?
Positive.
Are you sure?
Yes.
What's the sign of pi?
0. Are you sure? Positive or negative?
You're positive, it's positive. Yes. All right.
Or negative?
Okay. All strippers take cash. That is absolutely right. Okay. So, and good for life. So here we go. Our trapezoid for T sub 4 is going to be 1/2 times the width times, here we go, sum of the heights. We're not going to be lazy. We're going to write them out because we want full credit on the AP exam. Again, our two endpoint trapezoids are actually going to be triangles. That's okay. All right. When we clean, boy, everyone's very chatty. When we clean this up, we get pi eighths times root 2 plus 2 plus root 2. So we have 2 root 2 plus 2. So if you want to multiply the pi eighths in or pull a 2 out, whatever you want to do, right? So either way, you can have pi fourths root 2 plus pi fourths, or you could factor out a pi fourths times root 2 plus 1. I don't care. However you want to write it. Right? You could actually technically leave it like this, and that would be correct. Okay. You just can't have any unsimplified trig. Like, you can't leave your answer with a sign of pi fourths in it. You have to actually write what that is. Okay. So, sine. If only we knew the graph of sine.
But wait, we do know the graph.
But wait, we do know the graph of sine. From 0 to pi is sine concave up or concave down? Concave down. Therefore, this estimate is this going to be greater or less than the actual value? Estimate, so t sub 4 is less than the actual value because y equals sine x, or 6 is concave down on 0. Good. Okay. Any questions about trapezoids? Are you ready to do an AP problem?
Sure.
Okay. We're going to do 2010.
That's like 10 years ago.
That is almost 10 years ago.
I think this class might be on.
Okay. Okay. Oh, that's Ansky. Don't look. Okay. All right. Go away. All right. I'm going to read this to you first and give you a few little instructions. Oops. Stop coming back up. Let's see. Let's freeze. Freeze. All right. A zoo sponsored a one-day contest to name a new baby elephant. Yeah. Okay. Zoo visitors deposited entries in a special box between noon and 8 p.m. The number of entries in the box T hours after noon is modeled by a differentiable function E for entries from 0 to 8. Values of E in hundreds of entries at various times T are shown in the table above. So those are the numbers of entries in this box. It's a really big box. Okay. Part A. Use the data in the table to approximate the rate in hundreds of entries per hour at which entries are being deposited at time T equals 6. Show the computations that lead to your answer. I know you can all do this. Part B. Use a trapezoidal sum with 4 sub-intervals given by the table. Are these even widths, equal widths? No. So you're going to have to do each trapezoid separately, width times sum of the heights. Okay, you pull the half out, but that's all you can pull out. All right. To approximate the value of 1/8 times the integral from 0 to 8 of E of t dt. So they've got this 1/8 in front of the integral. Does the trapezoidal approximation approximate the whole thing, this whole 1/8 times the integral from 0 to 8?
No.
What does it approximate?
0 to 8.
Just the integral. So whatever you find for your trapezoidal approximation, you're going to have to multiply by 1/8 in order to get what they're asking for. You do not have to do this part where you explain the meaning because you haven't learned what this means yet. So this is something we will learn in the next unit when you take an integral and divide by this number. So anyway, we'll talk about that. But so you can, when you do part B, just do the first part, like part B sub part 1, right? Skip part B sub part 2. All right. Part C, you can do C and D. So let's talk C. At 8 p.m., volunteers begin to process the entries. They process the entries at a rate modeled by function P, where P is in hundreds of entries per hour from 8 to 12. According to the model, how many entries had not yet been processed by midnight, T equals 12? So let me ask you this. At 8 p.m., which is when they ended the contest, how many entries are in the box? 2,300. 2,300 entries are in the box at 8 p.m. because the table gives you number of entries in the box, right? Everyone okay with that?
I'm okay with that.
Okay, good. Okay, I'm glad you're okay with that.
I'm very okay with it.
Okay, so P of T is basically the rate that they're removing the entries from the box, right? So maybe we need to find the total number that they remove. I don't know. So maybe he's using something we've learned in this unit. So anyway, so that's for part C. And then part D, which I'm kind of curious if anyone gets this. So almost everyone in first period just skipped it. Please don't skip it. This is important. You're going to get tested on it, so it's good to know. According to the model from part C, At what time were entries being processed the fastest? So what are you really finding? You're finding a max of P, right? From 8 to 12. Okay, are we ready? Go. On your whiteboard. This is, oh, yes, wait, stop. This was question number 2. Is it calculator or no calculator? This is calculator. Okay, now you may begin.
I appreciate your dedication to work.
Part A is just derivative from a table. You go up 1, down 1, do slope of the secant or average rate of change. 4 hundredths of entries per hour. 4 hundredths of entries per hour is correct. I would have just said 400 entries per hour, but yes, that's fine. So it looks like, oops, okay. So you guys just got 400. Be careful, your units. No, for part A. I didn't say erase for part A, so be careful. So use the data table to approximate the rate in hundreds of entries per hour. So you either have to put 4 or you have to put 400 entries per hour, right? Okay. All right. So good. 4 with a number of hundreds entries per hour. That's fine. Okay. Same thing. All right. So everybody got it. You guys got the math. Just be careful with the units. Okay. So next, part B, trapezoidal sum. So just so you know, part A was only worth a point. All right. Part B, trapezoidal sum. The widths were not equal. What's the first width of your first trapezoid? 2, right? Because you're going 0 to 2. The next one you're going 2 to 5. What's the next width? 3, then 2, then 1. Okay. And then so it's width times sum of the height. So here's what you get. So ignoring the 1/8, they just bring that down. So they have first width, sum of the heights divided by 2. Next width, sum of the heights divided by 2, right? They wrote it in function notation. You can write it with numbers. That's fine. So if you write it with numbers, you're good. They went ahead. They never actually found the value of the trapezoidal sum. They went ahead and just found the divided by 8. This right here, whether you have it with function notation or numbers, that's worth a point. Then your answer with the division by 8 is worth a point. This last part I haven't taught you yet. So what does it mean? When you take an integral and divide it by the width of the interval over which you're integrating. Remember, area of a rectangle is width times height. So if an integral gives you area, so if we take the area, divide out the width, what we're left with essentially is a height. What is that height? Technically, it's the average height over the interval, or the average value of whatever function you've got in there over that interval. So what they're really saying is the average number of entries in the box is this in hundreds, right? So roughly 1,068.7, 1,068.8 entries were roughly, that's the average number of entries in the box from time 0 to time 8. So anyway, so that's that. But we haven't learned average value yet, so it's okay that you didn't know that, and I told you to skip it anyway. So that's why I was saying erase the units was for part B, ladies in the back, but not for part A. All right, part C. So at time 8 p.m., volunteers start to process the entries. They process at the rate P of T. How many entries had not yet been processed by midnight? Well, it would help if we knew how many had been processed by midnight. How many had been processed would be the integral from 8 to 12 of P of T, which all you need to do is write down the integral and then write down the answer. You do not have to integrate by hand, nor should you integrate by hand when you're holding a calculator. So that integral equals 16, but remember it's in hundreds, right? So from 8 p.m. to 12 p.m., they processed 1,600 entries. The question was, how many entries are left? Well, how many entries were in the box when they started processing? 2,300, because that was at 8 p.m. There were 2,300 entries in the box. From 8 to midnight, they processed 1,600. So how many are left? 700 entries, right? So part C was only worth 2 points. You got a point if you have this integral somewhere on your board. Woo-hoo! Okay, and then you got a point for the answer, which should have been 700. All right, so not 700. Yeah, good. Like, which I think almost everybody got. So, oops. Okay. Oh, you just subtracted 16. Yeah, you got to be so careful. I had that discussion with several people that hundreds is so important, right? Don't ignore the fact that it's in hundreds. All right. How do we find an absolute max or min on a closed interval? We find the derivative, we find the critical numbers, and we test the critical numbers and the endpoints, right? So we're finding the max value of P on the interval from 8 to 12. You got a point if somewhere on your board you wrote P prime equals 0. So if you have what P prime is, if you found P prime and wrote that equals 0, that's fine. That's equivalent, right? So well done. So you got a point if somewhere on your board you have to show, guys, whenever you're solving an equation, people tend to forget that setting a derivative equal to 0 and finding the critical numbers is solving an equation. You have to write equals 0. You got to write equals 0 next to your P prime or you don't get the point. So a point for showing that you set the derivative equal to 0, a point for finding the critical numbers, which you should have done on your calculator. That's such a shame. You guys are close. You found P prime. You never wrote equals 0 and you didn't find your critical numbers. You tested your endpoints though, so that's good. Okay, but this whole thing, the test and the final answer was all just worth 1 point. So anyway, so you had to, the big points here were for just finding, like setting the derivative equal to 0, finding the correct critical numbers. So anyway, when were they being processed the fastest was at midnight. Apparently they were like gaining speed all night. So anyway, so at midnight was when they had the max value. So you guys got the answer. You just don't have the right support, but you have the right answer.
We found it on our calculators instead of doing all that work.
Okay, that's great, except do you know how many points you get?
0.
0, yeah. So you guys have to, you can't have an answer with no supporting work. So you guys got it too. Ooh, and you have a test.
We didn't do that.
Oh, except you don't have your critical numbers. But because you have supporting work, I don't know, maybe they would still give you the point. I don't know. You might get a 1 out of 3. You get a point. You had 10.816 and 9.183. I personally would give you 2 out of 3. I don't know if the College Board would give you 2 out of 3 or 1 out of 3. I think they give you at least a point. Because they didn't show how they got the critical numbers. They didn't write the equation that they were solving, right? You always have to, if you solve an equation, you got to write the equation. Okay. So, all right, good work. Here's the thing. You all, well, we have 5 whole minutes. All right. We have 5 minutes for you guys to pull out quiz 5-2 and give me 5 more hearty minutes of work on it. All right? You're not going to finish it, but give me 5 more minutes of work on quiz 5-2 right now.